Sometimes, to understand ourselves, we need to look far back, to a place where there was no us, no earth, no light. Just stardust, drifting quietly through the boundless darkness. There, billions of years before we even breathed, a history we have almost forgotten was born. A history where stone learned to be a home, fire a sun, and has a harmony. We have become accustomed to the planet beneath our feet, but what seems eternal and solid to us was once liquid, hot, and disordered. Everything that seems familiar today, the sky, the water, the breath, didn't appear suddenly and not by chance. In this lecture, we will travel the path from the cosmic void to a living planet. We will examine how Earth could have been born according to science, myth, and perhaps by someone's will. And we will understand that perhaps our home is the most astonishing coincidence in the universe. Let this story carry you deep into time. Enjoy the journey, and let it be as calm as the breath of the earth itself. When the sun lit and the disk spun, before the earth was formed, before the first rain, before the first stones, and even before the very idea of a planet, nothing familiar existed. Space was empty and dark, like black velvet upon which the stars had not yet scattered. There was no light, no time, no horizon. Only fine dust, the dust of ancient stars, long dead and scattered into oblivion. This dust, fragments of carbon, oxygen, iron, silicon, descended from generations of stars that ended their journey in supernova explosions. Each such death exploded the star's interior outward and scattered across the galaxy all that from which worlds would one day be born. These atoms no longer remembered to whom they belonged. And yet, in the void, they were not dead. They held an opportunity. Somewhere in one of the spiral arms of the Milky Way, 27,000 light-years from the center of the galaxy, movement began. Perhaps it was a shock wave from another supernova explosion. Or perhaps the density of matter reached a critical value, and gravity began to pull the scattered matter into a coherent whole. Thus began a slow, almost imperceptible process of compression of a giant cloud of interstellar gas and dust. We call such clouds protostellar. They are the cradles of stars. Under the influence of gravity, matter began to be drawn toward the center. The denser the core became, the stronger its attraction. The temperature rose, the pressure increased, millions of years passed. At some point, conditions became sufficient to trigger thermonuclear reactions. Hydrogen atoms began to fuse into gels, releasing colossal amounts of energy. At that moment, the sun ignited. A young, furious, restless yellow dwarf, beginning its journey into eternity. The newborn sun was not calm. It emitted powerful streams of radiation, threw out plasma prominences, and blew the surrounding space with streams of solar wind. Everything around it was seething. But it was precisely these storms that cleared the inner part of the system of light gases, laying the foundation for the formation of rocky planets. A mass, the remnants of dust, gas, microscopic particles of ice and metals, swirled around the sun. This was the protoplanetary disk, a thin ring encircling the newborn star. It rotated, obeying gravity and the laws of conservation of angular momentum. Within it, delicate work was taking place. Dust grains collided, clumped together, and formed clumps. These clumps grew ever larger over time. The first objects to appear in this disk are called planetesimals. Their sizes ranged from a few kilometers to hundreds. They collided, collapsed, merged, and began to attract more and more matter. For millions of years, a fierce race raged. The largest would attract more and thus survive. This chaotic ballet of matter continued for hundreds of millions of years. Some of these bodies burned up, others were ejected from the solar system, but some remained. Gradually, future planets began to form within the disk. The inner region, closest to the Sun, became the birthplace of four rocky worlds: Mercury, Venus, Earth, and Mars. Here, it was too hot for ice and gas to persist. Only the heavy elements remained. Beyond the snow line, in the cooler part of the system, the gas giants began to coalesce from ice and hydrogen: Jupiter, Saturn, Uranus, and Neptune. They consumed everything around them at astonishing speed, growing to many times the mass of the inner worlds. But in one specific zone, within a narrow range of temperatures and distances from the star, something special was forming. Here, it was not too hot for water to evaporate, and not too cold for it to turn to ice. This habitable zone, as we call it today, became the birthplace of Earth. At this stage, it still had no face. It was a clod of dust and rock, gathering everything it could around itself. It grew, collided, and melted from the impacts. The temperature of its interior gradually increased. A core was forming within, iron heavy, dense. The Earth was taking shape. Meanwhile, the Sun continued its life, illuminating space and continuing to play a decisive role. Its gravity stabilized orbits. Its energy determined where metal would melt and where ice would survive. Its light became the pulse of the new system. Without the Sun, there would be no structure. Without structure, there would be no planets. Every stone, every drop of water, every molecule on Earth carries the memory of those first stars that died long before our system emerged. It all began with darkness, then with dust, then with fire. Thus the Sun was ignited. And so began the story of how Earth was born. When the Sun first flared up and began clearing the space around itself with streams of solar wind, a huge mass of debris, gas, and dust, a protoplanetary disk, remained rotating in this bright chaos. It was here, in the dusty ring around the young star, that the history of Earth began. The birth of our planet is not magic, but a chain of collisions. Dust grains left over from the formation of the Sun began to clump together. Millions of them. Each one is like a spark of design. They collide, stick together, grow. This is how the first planetesimals are born. Bodies the size of a mountain, then the village of Ostrov, and then a moon. They already have gravity. They don't just wander. They gather around themselves everything they can. In the area of today's Earth's orbit, conditions were harsh. Extreme heat, strong solar radiation, constant impacts. But this didn't stop the construction. Over millions of years, a group of bodies formed in this zone, which began colliding with each other with increasing frequency. One of these contenders for the title of planet was the embryo of Earth, not yet round, unstable, scarred from recent encounters with its neighbors. This phase is called accretion, when a body's mass increases by capturing other objects. At this time, the Earth is like a snowball rolling down a hill, dragging everything with it. It accumulates iron, nickel, and rock. Its mass grows. The force of gravity increases, and the impacts become more powerful. Each new fragment brings not only mass, but also heat. The body's interior begins to heat up. At this stage, an unspoken war was still raging between the nascent planets. Their orbits intersected. Each could become a planet, but space was limited. Those who captured the most emerged victorious. This is how our Earth began to dominate. It survived hundreds of impacts, was nearly destroyed, but survived and continued to grow. More than 4.5 billion years have passed since then, but we still bear the traces of this turbulent childhood. In the depths of the mantle are traces of ancient radioactive elements, the very same ones that decayed, releasing heat. The core contains a huge amount of iron, accumulated precisely during the era of early accretion. It was during this period that the Earth began to take shape. Under the influence of its own gravity, its matter compresses. The surface is still chaotic, but the center becomes dense. Differentiation occurs. Heavy elements sink deeper, lighter ones rise to the surface. This is the first step toward future structure. Core, mantle, crust. And yet, at this moment, the Earth is hell. There is no air, no water, no crust. It is a giant drop of molten rock, upon which meteorites rain from the sky. Imagine a world without a horizon, only fire, stone, and darkness. The temperature on the surface is over 1,500 degrees. This is not just heat, it is liquid rock, boiling metals. Thus the Earth was born. Not in silence or order, but in a frantic dance of destruction and creation. In a whirlwind of matter, gravity, and heat. First, it simply was, then it became. And in this becoming lay the first hint of the home we would one day call our own. But the real turning point in Earth's history would come a little later, when an uninvited guest entered its orbit. And then, the impact that changed everything would give it a satellite, the Moon. For now, our planet is merely a young, fiery heart beating in the darkness of an ancient solar system. Theia and the Moon, the impact that changed everything. When young Earth was just beginning its existence, it was not alone. The solar system of that time was in a state of instability. The planets had not yet established clear orbits. Fragments of protoplanets, fragments of ancient bodies, and the remnants of the gigantic collision that gave birth to the Sun and its family were everywhere. It was in this raging gravitational symphony that one of the most fateful episodes in the history of our planet occurred, the great impact of the planet Theia. This event is not just a hypothesis. It is one of the most compelling, dramatic, and, in its own way, poetic scientific theories about the origin of the Moon. According to calculations and models, about 4.5 billion years ago, a planet the size of Mars moved in an orbit intersecting with Earth. Scientists named it Theia after the ancient Greek Titan, mother of the goddess of the Moon. Theia and Earth were not enemies. Rather, they were dancers on intersecting trajectories. Their collision was a matter of time, and when it happened, Earth was already a molten inferno, but a thin crust was beginning to form. The first signs of structure were appearing. All of this was swept away in an instant. The collision occurred at an angle, not head-on, but glancingly, like a hammer blow to a ball. But the force was colossal. Both planets partially vaporized, their mantles ignited, and billions of tons of matter were ejected into near-Earth space. From this chaos, the Moon was born. This incredible satellite we see every night. Not an alien, not a fragment of an alien body, but the product of a terrifying yet familiar impact. Analysis of the composition of lunar rocks returned by the Apollo missions reveals a striking similarity to the Earth's mantle. This is one of the main pieces of evidence in favor of the Great Impact hypothesis. At first, a disk of debris, flaming droplets of magma, metallic fragments, and vaporized rock formed around the Earth. It rotated, compacted, and collided with itself. Thousands of years passed before these fragments, subject to gravity, coalesced into a single object. Perhaps the Moon initially had several cores, tiny proto-satellites, which over time merged into a single sphere. Initially, it was several times closer to the Earth than it is now. And in the sky, it was not just a bright point, but a dazzling giant, reflecting the primeval sun and the light of volcanoes. But it wasn't just its beauty. The Moon changed the Earth itself. First, it stabilized the tilt of our planet's rotational axis. Without it, the Earth would have wobbled more violently, like a toy top, and then the climate would have been unpredictable. Thanks to the Moon, the seasons became more stable. It tamed chaos, dampened extreme fluctuations, and helped the atmosphere form under relatively stable conditions. Secondly, the moon caused tides not only in the oceans, which did not yet exist, but also in the magma. The moon's gravitational waves caused the molten masses within the Earth to pulsate and mix. This stimulated geological activity, accelerated cooling, and formed the structure of the mantle. Thirdly, it was thanks to the moon that the future development of life acquired rhythm. When the first oceans later appeared on Earth, tides became not only a physical phenomenon, but also a biological impulse. Fluctuating water levels, the cyclical nature of moonlight, night, and day rhythms. All of this became part of the planet's genetic memory. Even today, we feel its influence. Without the moon, a day on Earth would last only 6 to 8 hours. Imagine how quickly days and nights would alternate, and how different biological development would be. Without the moon, we might not have the Earth as we know it. Thus, from fire, impact, and destruction, not only the moon emerged, but also the foundation for life. Theia disappeared, but its trace remains forever. Somewhere in the depths of the moon are traces of that very planet. Somewhere in the Earth, its dust lies beneath our feet. And every time we look at the night sky, we see the embodiment of the catastrophe that became the beginning of order. The chapter of Theia and the moon is a reminder. Even collision, even destruction, even the pain of the cosmos can become a source of harmony. When the Earth first breathed, the birth of atmosphere and waters. Imagine a scene where the world is just awakening, but not yet able to breathe. The young Earth, freshly surviving an impact, slowly cools after the thaws. The magma recedes, the surface cracks, and the breath of the planet rushes through the cracks into the sky. The first was poisonous, suffocating. But it was precisely this that marked the beginning of everything. Earth's primordial atmosphere had nothing in common with what we breathe today. It was a mixture of volcanic gases, carbon dioxide, ammonia, hydrogen sulfide, water vapor, methane. Oxygen, the very thing without which life cannot exist, was completely absent. The entire surface of the planet was teeming with volcanoes, and each one erupted not only lava, but also entire clouds of gas, swirling in the sky into dense clouds. It was believed that Earth, like other terrestrial planets, lost its very first atmosphere, light and thin, to the solar wind. The young sun then had an explosive nature. It emitted streams of particles that tore away everything that couldn't hide behind a magnetic shield. And Earth didn't yet have a full-fledged magnetic field. Therefore, a new atmosphere emerged from within, from magma, from the depths where water and gases remained after the planet's formation. And now the sky is heavy with steam, and the Earth, like a giant kettle, boils from within. Gradually, the atmosphere becomes saturated with water vapor. It rises, thickens, and falls again as rain, but the Earth's surface is still too hot to retain the water. It evaporates and rises again. This cycle repeats for millennia. The origin of water is a great mystery. Where did water come from on Earth? The scientific community offers several hypotheses, none of which excludes the others. The common hypothesis: water could have been brought to Earth from the depths of space by icy bodies or comets. However, this food has a problem. Water on comets often has a different isotopic composition than water on Earth. Nevertheless, some of the material could well have arrived this way, especially during the late heavy bombardment. Asteroids and meteorites. Carbonaceous chondrites are ancient meteorites containing not only water, but also organic matter, chemically closer to water on Earth. Therefore, many scientists are inclined to believe that they, not comets, were the main suppliers of water. Internal origin. Perhaps most of the water was locked inside the Earth from the very beginning. deep mantle minerals could have retained the water, and later, through volcanic activity, it began to escape. Whatever the case, at a certain point, the vapor in the atmosphere became so abundant that it could no longer remain a gas. The first great rain began, and it lasted for thousands of years. It was an unusual rain as we know it. It was acidic, heavy, accumulating in pits and cracks, only to evaporate again in the heat of the magma. But gradually the crust cooled, and at some point the water remained. The earth began to retain the liquid. Thus, the first puddles appeared, then lakes, then oceans. The primordial ocean, black, lifeless, boiling. The first ocean was far from the pictures in textbooks. It was black, dense, saturated with minerals and chemicals. Water boiled near underwater volcanoes. The seafloor spewed jets of hot gases and metals. A methane sky shrouded the ocean, through which the weak light of the sun barely penetrated. But it was in this water, saturated with chemical elements, that, under the influence of temperature and pressure, the first reactions would begin that led to the emergence of life. This was the birthplace of all life, the liquid cradle of the world, the moon, and the stabilization of the climate. It is worth mentioning that the Earth's climate and atmosphere were influenced not only by its own activity. The moon, formed after the impact, began to play a critical role in stabilizing the Earth's axis. Without it, the planet could have experienced sharp climatic fluctuations, from hot greenhouse conditions to glacial deserts. The moon helped keep the climate more or less stable, and therefore offered a chance for a stable hydrosphere. Thus, the atmosphere and water appeared almost simultaneously, and were the result of internal processes, external impacts, and a long cooling period. The Earth breathed for the first time. First, poison, then moisture, and one day, oxygen. But that is still a long way off. Now our planet is a black ocean, a volcanic crust, an acidic sky. And in this darkness, something important is already happening. The next chapter is about how the crust came into being. Not just a surface, but the foundation for continents, mountains, and landmasses. The Earth is already breathing. Soon it will begin to build. When the Earth gained a face, the first crust due to the birth of the continents, when the oceans first stopped evaporating into the void and began to linger on the surface, when volcanoes continued to erupt, but between the lava flows there were intervals of calm, then the Earth gained something that could be called a face. It was unlike ours, cracked, scarred, and blazing, but already stable in some primordial sense. The formation of the Earth's crust had begun. A fine line between hell and continent. The first crust was not a solid foundation, more like a thin, fragile crust on a planet raging with lava. Scientists call this stage the igneous or primary crust. Its composition differed from what we see today. These were predominantly basaltic rocks, dark, dense, and heavy. They formed during the cooling of the lava, and were very quickly drawn back into the depths by subsequent movements of the mantle. At this stage, only scattered islands of solidity existed. There were no permanent continents. The lithosphere, the planet's solid shell, was still just forming, and beneath it, mantle currents raged, creating areas of stretching and compression. Periodically, sections of the bark broke, sank, and overlapped each other. Thus began the era of tectonics. Approximately 4 billion years ago, a key event occurred. The first stable continental crust emerged. Unlike oceanic crust, which was dense and sinking, it was lighter. Its composition was dominated by granite and silicates. It did not sink into the mantle, but remained on the surface. These were the first floating islands of land, not sinking in the seas. The Archean is the age of the most ancient lands. This period is the geological era known as the Archean. It spans the time period from 4 to 2 billion years ago, an era when the Earth was just beginning to come together. During the Archean, so-called crotons, stable areas of ancient continental crust, appeared. They exist to this day and form the basis of modern continents. For example, the Canadian Shield or the Australian Platform are parts of those very same pristine land masses. The formation of these structures was accompanied by powerful volcanic activity, metamorphism, the alteration of rocks under pressure and temperature, and the accumulation of sedimentary rocks in shallow seas. The processes were chaotic, but they already revealed the rhythm of the future Earth. How the continents were formed, the tectonic puzzle. At the dawn of the planet, there was no stable system of continental plates. The Earth's surface was more like a patchwork quilt of tiny blocks that collided, broke apart, and then stuck together again. This process, terrain accretion, took millions of years. Small fragments of crust adhered to larger ones, creating the prototypes of continents. Over time, these blocks coalesced, forming protocontinents. One of these ancient ones is Volbara, believed to have existed about 3 billion years ago. Then came Uar, and later Conarland and Columbia. Each of them assembled, crumbled, and gave birth to the next. The continents of the early Earth weren't stable land masses. They floated, collided, and then drifted apart again. It was a great tectonic waltz, an endless churning of rock and heat. And beneath this waltz, the mantle churned, moving them along an unknown plane. Traces of ancient land. Amazingly, traces of these ancient processes have been preserved on our planet. The oldest outcrops of the Earth's crust, for example, rocks in Canada, are almost 4 billion years old. There, you can literally touch rocks that formed when the Earth had no air and the oceans were acidic. Another striking region is the Isomosy region in Greenland, where scientists have discovered the remains of sedimentary rocks with suspected traces of ancient life. If this is definitively confirmed, it was here, in the silence of ancient granite, that life began to write the first lines of its history. Sea and land, the first boundary. When a stable crust appeared, and upon it the first land masses, the first boundary emerged. The boundary between ocean and solid ground. It was this boundary that would soon become the scene of the greatest event, the emergence of life. But while Earth was still learning to be a planet, its face had not yet acquired its familiar features. It was a planet without forests, without rivers, without animals. Only lava plains, Archean shields, sulfur pools, and silent skies. Earth did not yet know that one day cities would appear on these rocks. From minerals to molecules, chemical evolution. The planet had already acquired a face. It had a sky, albeit one alien to us. Clumps of ammonia, methane, dioxide, carbon. There was water, not the gentle expanse of the sea, but boiling, evaporating oceans, saturated with metals and acids. There is stone, the primordial rocks that have survived billions of years of tectonic upheavals, but the essential element of life is missing. Life is not yet a gift from without, but the result of a long chemical symphony. This chapter is about the first spark, ignited not by divine inspiration, but by the earth itself. A chemical soup, a primordial ocean of possibilities. Scientists call it the primordial soup, a world ocean rich in dissolved minerals, metals, and inorganic compounds. It contains ammonia, hydrogen sulfide, cyanides, carbon dioxide, water vapor, and iron and manganese ions washed out of volcanoes and crustal faults. Water temperatures could reach hundreds of degrees near underwater springs. These were hydrothermal vents, black smokers spewing out streams of hot, mineral-rich water. It was there, according to one theory, that the first reactions occurred that led to the emergence of life. But perhaps it all didn't begin in the abyss. There is another hypothesis. Drying lagoons and shallow, warm pools on the surface of Archean continents, where the concentration of substances reached its maximum. The chemistry of life could have unfolded there. Amino acids, the ABCs of biology. In 1953, two scientists, Stanley Miller and Harold Urey, decided to reproduce the conditions of early Earth in the laboratory. They took a mixture of gases, methane, ammonia, water vapor, and hydrogen, and passed electric discharges through it, simulating lightning. A few days later, they discovered amino acids, the building blocks of proteins, in the liquid. This became a scientific sensation. The simple conditions of early Earth were capable of generating complex molecules. But one discovery wasn't enough. Where and how did these molecules assemble into something more? Chaosorbates, microscopic droplets resembling the simplest cells, came into play. They form when certain polymers, such as proteins or nucleic acids, spontaneously assemble into droplets surrounded by a semi-permeable shell. Chaosorbates were not living organisms, but they already had a metabolic boundary and responded to the external environment. This was the first hint of cellularity. At the same time, the RNA world theory was developing. In it, RNA, ribonucleic acid, plays a key role. It is capable of storing information like DNA and catalyzing reactions like proteins. Scientists discovered ribozymes and RNA structures that function as enzymes. This suggested that at the dawn of life, self-replicating RNA chains existed. It is this idea that RNA could have been the first molecule of life that unites many approaches. Minerals as the cradle of life. But how could such molecules have arisen in a chaotic ocean? This is where clay minerals come into play, in particular marlinite. Their crystalline structure is capable of absorbing organic molecules, arranging them into chains, and protecting them from destruction. Laboratory studies have shown that on such surfaces, amino acids more easily combine into peptides, and nucleotides into RNA. In other words, the stone may have been not a barrier, but a midwife for the first forms of life. Theories of the origin of life are debated without a winner. Modern science identifies several leading hypotheses. The hydrothermal vent hypothesis. Life originated near hot rifts on the ocean floor, where there was abundant chemical energy. The shallow water hypothesis. Life arose on the surface, where evaporation, sunlight, and changing humidity created unique conditions. RNA. Life began with self-replicating RNA, and later DNA and proteins diversified. A mineral matrix. Life formed on clays and crystals, which stabilized complex molecules. Panspermia. Life was brought from space on meteorites, such as those found in Antarctica and presumably of Martian origin. None of the hypotheses yet provides a definitive answer, but they all point to one thing. Life is not a miracle, but a logical continuation of chemistry, begun by the stars and completed by the oceans, from molecules to life. The transition from chemistry to biology did not happen overnight. It was a long process, perhaps lasting millions of years, where chance and regularity went hand in hand. Some chains proved stable, others capable of being replicated. Somewhere, the simplest mechanisms of digestion and the absorption of external molecules appeared. Thus, protocells were born, the first organisms, not yet fully alive, but already distinct from inanimate matter. And it was they who would lay the foundations of the biosphere, which would change the planet beyond recognition. When life, archaea, bacteria, and photosynthesis appeared. If you've ever wondered when Earth first learned that there was life, it likely happened quietly, without a bang, without a flash of insight. Somewhere in warm water, in a crevice of volcanic rock, or in a shallow lagoon, the first creature appeared. A truly living creature. It didn't think, didn't breathe, didn't feel, but it divided, it reproduced, and it lived. The very first archaea and bacteria. Modern genetic and biochemical research indicates that life on Earth emerged approximately 4 billion years ago. This happened quite quickly after the crust formed and the ocean stabilized. The first life forms were single-celled. Without a nucleus, they were prokaryotes, namely archaea and bacteria. Archaea are creatures that still live where nothing else can survive, in boiling geysers, acidic lakes, on the ocean floor under kilometers of water. Their metabolism is unusual, their genes are ancient. Scientists believe that archaea are descendants of the very first organisms. Perhaps they were the first to learn to harness the chemical energy of hydrogen sulfide and methane in the depths of ocean vents. Bacteria, on the other hand, became masters of ubiquitous survival. They are less extreme, but far more diverse. From an early stage, they began to master photosynthesis and changed everything. Photosynthesis is the catastrophe that gave birth to life. Imagine Earth 4 billion years ago without oxygen, with a thick atmosphere of methane, ammonia, and carbon dioxide. It was impossible to breathe, impossible to burn. This was the world before fire and breathing. Then, some bacteria learned to capture light and use it to convert carbon dioxide into organic matter. These were cyanobacteria, blue-green algae living in warm water. As a byproduct of photosynthesis, they began to release oxygen. Oxygen broke down molecules, blocked enzymes, killed organisms. Many ancient bacteria disappeared and remained only in dark, oxygen-free niches, deep underground, in volcanic vents, under the ice. But it was precisely this crisis that paved the way for aerobic life. New creatures emerged that learned to use oxygen for energy, and this proved much more efficient than previous methods. Thus began the oxygen apocalypse and, simultaneously, the first great transformation of Earth, the oxygen catastrophe in iron ores. The scale of the changes is difficult to imagine. The released oxygen initially did not enter the atmosphere. It reacted with iron dissolved in the oceans. This led to the formation of huge layers of iron ore, known as banded iron formations. They are still mined on every continent. Only when the iron was saturated did oxygen begin to accumulate in the atmosphere, and by 2 billion years ago, oxygen levels could already be measured. This event is called the Great Oxygen Catastrophe. The old world died. A new era began. Life did not stop. On the contrary, it learned to be flexible. The first organisms learned to exchange genes. Horizontal transfer, when one cell literally inserts a fragment of foreign DNA into its own. This accelerated evolution hundreds of times. A bacterium capable of surviving radiation hundreds of times higher than the lethal dose for humans. Methanogens, archaea, live in the gut and swamps. Cyanobacteria still photosynthesize in lakes and oceans. The world we live in began with them. Fossil traces of the first stromatolites. In Western Australia, in the Shark Bay area, you can see unusual stone domes protruding from the water. These are stromatolites, the oldest evidence of life, created by layers of microorganisms. They still exist today, but their ancestors left traces more than 3.5 billion years old. Each layer represents a growth cycle season after season. Stone pages that tell of a time when on Earth there was nothing living except bacteria. Archaea and bacteria dominated the Earth, almost 2 billion years. This is the longest era of life, quiet and unnoticeable. There were no eyes, no nerves, no death as we know it. But in their microscopic world, selection was already underway. Stable mutations were already appearing, the first communities were already forming, biofilms, tiny colonies, protected by a mucus matrix. This was the first step toward organization. And where organization appears, complexity sooner or later arises, and soon a new form of cell, a cell with a nucleus, will appear on the scene. But that's the story of the next chapter. The oxygen catastrophe, how life nearly destroyed itself. Imagine a world where the sky is copper-colored, the oceans dark green, and the air a mixture of toxic gases. No birdsong, no animal breathing, no rustling of trees, because neither birds nor trees yet exist. This is Earth 3 billion years ago. And in this strange silence, microscopic creatures quietly wander, hiding in drops of water, in rock crevices, in sulfur springs. They don't need oxygen. In fact, it's deadly to them. Life in that era flourished in completely different conditions. The atmosphere consisted of methane, ammonia, hydrogen, and carbon dioxide. It was a world of anaerobes, organisms that not only didn't need oxygen, but were killed by its presence. Their metabolism was structured differently. They used sulfur, iron, and hydrogen to generate energy. All was calm for a while, but then something changed. On the ocean floor, in warm, illuminated shallow waters, tiny, strange creatures called cyanobacteria appeared. They didn't need volcanic gases or deep-sea vents. They learned to harness the energy of the sun and revolutionized life. They learned photosynthesis. Unlike modern plants, cyanobacteria were primitive. They had no nuclei, leaves, or roots. But they accomplished the most important thing. They began releasing oxygen as a byproduct of their photochemistry. It was a waste product, a byproduct gas they didn't need. So they simply dumped it into the water. For thousands of years, nothing. Millions, almost no change. The oceans absorbed oxygen, saturated it with minerals. The iron in the water literally rusted. It was during this period that the famous banded iron ores, rich in oxides, that we mine today, were formed. But there will come a time when the oceans will say, "Enough!" At first, oxygen simply disappeared into the seas, reacting with iron and other substances. But soon all the reduced minerals were saturated. A turning point had begun. Oxygen could no longer dissolve without a trace. It began to leak into the atmosphere. And this was a catastrophe. It was the end for the entire former world. Anaerobic organisms, accustomed to the mild, reduced world, suddenly faced poison. Oxygen destroyed their membranes, damaged proteins, and caused mutations. A mass extinction swept the planet. Billions of microbes perished, entire ecosystems disappeared. The oxygen revolution turned out to be the greatest crisis in the history of early Earth. This event is known as the Great Oxidation Catastrophe. It occurred approximately 2 billion years ago. Scientists call this moment the Archean boundary. Proterozoic. Geochemical data confirms that it was precisely at this point that traces of free oxygen began to appear in the oldest rock layers. It began to change everything: the atmosphere, the chemistry of the oceans, the climate. One of the consequences was a global freeze. Methane, a powerful greenhouse gas, began to break down under the influence of oxygen. The planet cooled. It was likely then that the first snowland began, an era when glaciers could even reach the equator. And all this because of tiny photosynthetic microbes. But a catastrophe for some, an opportunity for others. Some organisms adapted. They developed detoxification mechanisms. They learned to use oxygen not as a poison, but as a fuel. This was an incredible step. Aerobic metabolism proved to be dozens of times more efficient than anaerobic metabolism. Evolution opened new horizons, new life forms emerged. Those who could survive in a world of oxygen gained an advantage. They spread, they captured niches, and created the foundations of future ecosystems. The slow but inexorable preparation for the emergence of complex eukaryotic cells began. Oxygen became an ally, not an enemy. It opened the way to something greater, to complexity, to intelligence. But then, at that moment, everything looked different. The planet was shaking. One world was dying. Another did not yet understand that it was only just beginning to be born. This is the irony of life. The most massive catastrophes become its engines. The oxygen catastrophe is one of the greatest transformations in Earth's history. A small organism and a great shift. Slow photosynthesis and global freezing, gases and the basis of respiration. This is how evolution works. By destroying, it creates. By killing, it frees up space. And those who survive will change everything. This is precisely what will happen one day in the next chapter, where we will encounter the first great change in form and learn how life learned to unite into something more than just a cell, snowballs and explosions. Earth in a fever. Imagine a planet that has experienced a great awakening. It filled with oxygen, became covered with the first microscopic inhabitants, learned to exhale, and suddenly froze completely all the way to the equator. A kilometer-thick ice shell encased the Earth in a white prison. Not a drop of rain, not a splash of waves, only ice. Welcome to one of the most mysterious periods in the history of our planet, the era of Snowball Earth. The Snowball Earth hypothesis. According to this hypothesis, Earth experienced at least two phases of almost complete global glaciation. The oceans became covered in ice, and glaciers slid all the way to the equator. Climatologists have dubbed this phenomenon snowballs, or snowball Earth. But how could this have happened? There could have been several reasons. We already know one of them, the oxygen catastrophe. When cyanobacteria began filling the atmosphere with oxygen, they displaced methane, a greenhouse gas that had previously trapped heat. Without methane, temperatures dropped sharply. Other theories suggest a shift in the position of the continents. As land moved closer to the equator, weathering increased, which also reduced the amount of CO in the atmosphere. Fewer greenhouse gases, a colder climate. But the Earth didn't just freeze. It seemed to enter a cold spell. Sunlight reflected off the sparkling icy surface, not being retained in the atmosphere. The albedo effect, a positive feedback where cold generates even more cold, emerged. The ice expanded, rivers and seas solidified, and precipitation ceased. It was an ice apocalypse. And yet, life did not disappear. Scientists suggest that volcanoes continue to function, releasing CO into the atmosphere. This process was slow but inexorable. For millions of years, volcanoes increased the concentration of carbon dioxide in the atmosphere. Until a tipping point occurred, the greenhouse effect warmed the planet. The ice melted, and the Earth began to breathe again. This great warming left behind traces in the form of rocky deposits, with alternating layers of ice and tropical minerals, confirming the dramatic climate pendulum. But it wasn't only ice that disturbed Earth's peace. Much earlier, about 4 billion years ago, our planet was subjected to another test, the Late Heavy Bombardment. This was the period of the cosmic storm. For hundreds of millions of years, meteorites and asteroids rained down on Earth, the Moon, Mars, and other bodies in the solar system. These weren't isolated impacts. They were a veritable cosmic artillery barrage. Why did this happen? One of the leading hypotheses is the migration of gas giants. Jupiter and Saturn, as they shifted their orbits, disrupted the gravitational balance in the asteroid belt. Rocky chunks tens of kilometers in size were torn loose and headed toward the inner planets. Many of them crashed into the Earth, creating craters, evaporating oceans, and heating up the atmosphere. Some scientists even speculate that some of Earth's water may have arrived with comets during this era. The Cambrian explosion. Now let's imagine the opposite scenario. After centuries of cold and darkness, the Earth begins to warm, the ice melts. The atmosphere becomes saturated with steam. Volcanoes breathe more actively. The oceans fill with salts and nutrients. And then, suddenly, the Cambrian explosion occurs. This event is not a literal explosion. Rather, it is an explosion of life forms that occurred about 541 million years ago. Almost suddenly, on a geological scale, the Earth became populated by complex organisms. Skeletons, limbs, mouths, eyes appeared. What had previously developed in the silence of microscopy now filled the seas with veritable monsters. The Cambrian fauna was bizarre and exotic, including marine predators up to a meter long with tentacles on the Malacaris, Apabini with 5 eyes, 3 labbits covered in armor. All this seemed to have come from a fantastic dream. For the first time, organisms learned to move, hunt, and defend themselves. Sexual reproduction emerged, which accelerated evolution. And for the first time, an ecosystem emerged in which predators and prey coexisted. Why did this happen then? The answer is still unclear. Some theories suggest reaching the oxygen threshold, when organisms became more energy efficient. Others speak of a genetic revolution, the accumulation of DNA codes that allowed for the construction of complex bodies. Perhaps the retreat of the ice after Snowball Earth gave the biosphere a chance to expand. The Cambrian explosion was the starting point for all complex life. Without it, there would have been no fish, plants, dinosaurs, mammals, or us. It wasn't just a surge of evolution. It was the rebirth of Earth as a living planet, with the emergence of humans. Imagine a deep river of time, flowing slowly and stubbornly through billions of years. In this river are chemistry and rock, dust and lightning, microorganisms and glaciers, explosions of life and catastrophes. But one day, a creature emerged from this ancient river, raising its head to the sky for the first time and asking, "Who am I?" Thus man was born. But the path to this was long and arduous. Life, originating in the warm ocean broth, was for a long time modest. Single-celled bacteria, algae, the first multicellular organisms appeared approximately 800 million years ago. They were soft-bodied creatures, resembling sacs or feathery leaves. They didn't hunt, didn't crawl, and had no eyes. After the Cambrian explosion, everything changed. The world became filled with movement, shells, and predators. At first, invertebrates dominated, then fish with jaws. They became the first vertebrates, beginning the chain that led to humans. About 400 million years ago, fish began to colonize land. Their fins gradually turned into limbs, their breathing bladders into lungs. Amphibians appeared, then reptiles. Some of these became the ancestors of dinosaurs, others the ancestors of mammals. When mammals first appeared, they were small and nocturnal. Their time came only after the Great Extinction, 66 million years ago, when an asteroid wiped out the dinosaurs. It was then that mammals occupied the vacated ecological niches. Primates evolved from the first rodents and insectivores over millions of years. They were distinguished by large brains, forward-facing eyes, grasping hands, and prehensile appendages. Among them, about 7 million years ago, the first representative of the genus that would later lead to humans appeared. Neanderthals, Denisovans, Cro-Magnons. All of them left their mark on our genetics. Modern humans are not the product of a single leap, but a mosaic of thousands of generations, stitched together by time and selection. At first glance, it may seem that geology and biology are two different histories. The former speaks the language of tectonic plates and volcanoes, the latter of cells and genes. But in fact, they are inextricably linked. Continental fissures and mountain building created new ecosystems. Ice ages and volcanic eruptions triggered mass extinctions, after which life began a new chapter. Atmospheric composition, ocean temperature, tectonic movements. All of this influenced the direction of evolution. For example, the rise of the Tibetan Plateau influenced the monsoon climate and the evolution of herbivores in Asia. The closure of the Isthmus of Panama altered the Gulf Stream and triggered the glaciation cycle in Europe. Even the location of Africa and its aridity forced human ancestors to descend from the trees and begin walking on two legs. We are born of stone and wind, mountains and seas. Our history is geology in motion, but with a beating heart. Humans are children of the earth. We carry within us the iron of ancient stars, the water of ancient oceans, and the warmth of the primordial sun. We are the result of billions of coincidences and adaptations. We have eyes capable of seeing light reflected from the moon, and a brain capable of pondering the meaning of time. We build cities on tectonic plates, fly into the sky, dive into the oceans. But we still depend on the planet's breath, on its soil, climate, water, and rhythms. Humanity can change the earth and already is, but it cannot separate itself from it. We are not outside nature. We are its voice and, perhaps, its memory. The geological record continues. The next chapter is ours, and what we write in it will be meaningful not only for us, but also for those who come after. We have passed through billions of years, compressed to a point, and expanded into the universe. We have peered into a volcano and into DNA, seen how order is formed from Hasa. But now we are faced not with a scientific, but a philosophical question. What does all this mean for us, creatures who can look back? Consciousness as a continuation of evolution. When we speak of the mind, we rarely remember that it is a biological organ, like the heart or the liver. Consciousness arose not in spite of nature, but because of it. It is its latest form of organization of matter to date. Through billions of trial and error, from dirt and dust, from amino acids and meteorite impacts, the earth gave birth not just to life, it gave birth to thought. Every thought is the movement of electricity in a protein cell. Every impulse of kindness, every act of love, doubt, inspiration, it's the work of a brain created by volcanoes, oceans, chance, and time. Consciousness is nature aware of itself. But to be conscious means not only seeing, it means understanding the consequences. We live in an age when humans are capable of changing the climate, drying up rivers, and burning forests. We are no longer simply inhabitants of the earth. We have become its evolutionary factors. For the first time in the history of the planet, a species has emerged that can understand the scale of time. We know that the sun will one day go out, that life can disappear, that ecosystems are fragile. We can build models of the future and remember the mistakes of the past. And we face the question, who will we be in this new chapter of the geological record? Creators or destroyers? A transitional form or a point in biological progress? A philosophy of belonging? Can one feel part of something so vast? The Earth is not just a planet. This is our only home, our body, our parent. Every cell in us bears the traces of past eras. The iron in our blood comes from supernova explosions. The calcium in our bones from petrified seas. We don't live on the Earth. We live within it. We are its innermost layer, thinking and beating. To understand this means to rid ourselves of the illusion of separateness. We are not against nature. We are its continuation, and perhaps its hope. And now, when you close your eyes, imagine, beneath you are kilometers of rock layers, millions of years of history, traces of life. Fossilized shells, grains of pollen, dinosaur bones, and above you are the stars in which your atoms were once born, and you are the bridge between them. Your thought is the connection between heaven and earth. And there is nothing accidental about this. Good night. You are part of something great, and this requires no proof. Only breathing.